we need to remember what the definition of a function is. And we know that a function is a special type of relation that assigns each element in the domain to exactly one element of the range, which means for every value of x, there's only one value of y. And we came up with a bunch of different tests that we can use to check that. So when we know a relation is a function, we can use special notation called function notation, and that's what you're going to see moving forward in math and in your textbook this year, in university, etc. So in order to explain function notation, it's easier to explain the function just sort of like a machine. So we're going to work with this function here, y equals 2x plus 1. We know it's a function because it's a linear relation. It has a slope of 2 and a y-intercept of 1, and so it's not going to be a vertical line, therefore it is going to be a function. So we're going to think of it as a machine by thinking of x as what we're inputting and y as our output, so what we get. So when we plug in an x, what pops out for y? So inside the machine here is our actual function, and this function is, in this case, 2x plus 1. So in this machine, an x is getting inputted, then it's getting multiplied by 2, and then it's getting added by 1, and that's what's going to pop out our y. And so let's go ahead and do some examples. So inside here, I'm also going to put in 2x plus 1, 2x plus 1, because that's the function we're dealing with. So in this case, if I were to input a 3, it's a very simple question that you could have answered even before grade 9. What that really means is take the 3, multiply it by 2, and then add 1, and what do we get? Well, 2 times 3 is 6, plus 1 is 7, so our output is going to be 7. Let's do this example here. So when I plug in a -2, I'm going to replace -2 with x. It's going to get multiplied by 2 and then added 1. 2 times -2 is -4, plus 1 is going to be -3. So let's just summarize it down here. So when we inputted a 3 into our function machine, we will get only one output because that's the definition of a function, and in this case it's 7. So the output was 7. And when we inputted a -2, we got the output of -3. So you might be thinking, why are we taking this very simple concept of a linear relation and breaking it down this way, like a machine? Well, thinking about a function as a machine with inputs and outputs are going to help us to better understand function notation and what it really means. So we're going to see a lot of this little sort of symbol that says F bracket and an X and an N bracket. And what that's actually pronounced as is F at x. So this f with an x beside it is not actually f times x, it's called f at x. And now we can replace f at x with y. So if we know that a relation is a function, like this linear relation here, we know a linear relation is always going to be a function as long as it doesn't have an undefined slope, we can replace y with f at x. And f at x means that y is a function of x, meaning we input the x and we're going to get out the y. Another way to say that is y depends on x. Again, we're inputting an x and we're getting a value for y. So in conclusion, we can replace y with f at x when the relation is a function. So let's just practice down here. We know that we worked with this relation here. We know it's a function. Therefore, instead of writing y equals 2x plus 1, we can instead replace the y with f at x. And so we can write f at x is equal to 2x plus 1. And it really means the same thing. The added difference is that we know that because it's written in this notation, it must be a function. An added benefit of writing equations this way when we know a relation is a function is that when we actually plug something in for x and we get a solution, we have more information in that solution. So for example, this is a very simple problem that you would have done in grade 9. Given this equation that we had, which was, let me write it down, y equals 2x plus 1. Here this question has asked, what is y, or what is the function equal to when x is equal to 3? So instead of starting off with y equals 2x plus 1, we can change the y to f at x, and that's what was done here. And if I know when x is we want to find when x is equal to 3, just like in grade 9, every time we see an x, we're going to replace it with 3. Not only in the equation here, but also in the function notation over here. So instead of writing f at x, we're going to say f at 3. And what that means is we are plugging 3 into the function f. So now f stands for this function, the multiplying by 2 and then adding by 1, and that x represents the input. So we're inputting 3 into the function f, and this is what we're going to get. We're going to get 2 times our input 3 plus 1, and that's going to be 7. So that's the basic idea of using function notation. Instead of writing y, we're going to replace it with f at x, and when we plug in a value or an expression in for x, we're going to plug it in like we always do, replacing x, but we're also going to replace it in this function notation here. So in our final solution, instead of the final solution just writing y equals 7, which doesn't give us a lot of information, we actually have a point. We know that when x is equal to 3, y is equal to 7. So that we know that on this function, the point 3, 7 must exist. So let's check how much you understand by trying a few simple examples. So in example 1, we're given the function negative 3x plus 1. We know it's a function, again, because it's a linear relation. And we are asked to determine f at 4 and f at negative 2. So let's break down what does f at 4 really mean, and what does f at negative 2 really mean? Well, this is in the place of x. So what this actually means is, what is the value of the function when 4 is plugged into the function? So we're going to write, what is the value of the function, I'm just going to use f, when x is equal to 4. Another way to think about that is, what is the value of y when x is equal to 4? So we're going to write it that way for the next guy. If this is easier to understand, now we're going to plug in negative 2 into the function. So what that means is, what's the value of the function? Meaning, what's the value of y when x is equal to negative 2? So what is the value of y when x is equal to negative 2. So these are the exact same things, value of x and value of y, they're equal. So to find these, you'll get really, really fast at it. To start off, I'm just going to start off with the original function, which is f at x equals negative 3x plus 1. Then I'm going to find f at 4. That means that every time I see an x, I'm going to replace it with a 4. So I have f at 4 is equals, I've got a negative 3, copy the negative 3. We're going to replace the x, we're just plugging in x is equal to 4, and then we've got a plus 1. So we know that f at 4 is equal to negative 3 times 4, that's negative 12, plus 1 is negative 11. So we have f at 4 is equal to negative 11. So we know that the point 4, negative 11 must be on this function. So again, 4 is our x value and negative 11 is our y value. So very, very quickly, let's also find f at negative 2. So again, I'm going to start off with the original function. We have f at x equals negative 3x plus 1. And now we're going to plug in negative 2. So f at negative 2 is equal to negative 3, instead of x, we're putting in negative 2, and then we have plus 1, and we know that that is going to equal to 7. So we have another point that we know is going to be on the function. When x is negative 2, y is equal to 7. In example 2, we're given a new function. This time it's called h at x, and it's linear, equals 3x minus 2. So we've been using f at x because f stands for function, but you don't have to name the function f. You can name the function whatever you want. So in this case, this person named it h. But remember, it all means the same thing. So h at x really just means y equals 3x minus 2. These are completely equivalent. So while you're getting the hang of this, if you consistently need to change your f at x or h at x to y to understand what's going on, that's absolutely fine. So in this question, we're given this relation y equals 3x minus 2. It's called h, so we know it's a function, so we're going to call this y h at x, and it's asking us to find a whole bunch of different values for x. So let's work on them one at a time. So the first one should be familiar to us. This is asking for what is h at -1. Remember, that's not h times -1. H stands for this function over here. So we know from last time that this must be our x value. So we're going to start off with our original function, h at x equals 3x minus 2, and we're going to plug in -1 for x. So that's all we're doing. Grade 9 problem. We're just, what's y when x is -1? So we have 3 times -1 minus 2. And we have h at -1 is equal to -5. Okay, so if we wanted to write that out as a point, we know that the point -1, 5 must be on this function. So now this one looks a little odd. This is asking for h at a. So instead of x, we have an a in its place, which means that we're just switching the variable. All that this question is asking for is what's the value of the function when I replace x with a. So whatever is in here, we're going to replace x with it. So I'm going to remind you what the function is. Our original function is h at x is equal to 3x minus 2. And now we're just plugging in a for x. So it seems weird, but just go with it. Instead of x, we're going to write a. We have equals 3. And again, instead of x, we're going to write a minus 2. And now take a look at this. Is there anything else you can simplify? And that answer is no. We're completely done. This is our final answer. So just remember, whatever is inside these brackets here, that's what we're going to plug into the function. That's what we're going to replace x with. All right, let's keep going and make it slightly harder. Now this question is saying, what if we were to take the function and plug in x plus 5? So that's really just a transformation. We'll talk about that later. But what this means is we're finding h at x plus 5. So that means that every time we see an x, we're going to replace it with x plus 5. So that's exactly what we're going to do. So let's start off with the original equation. We have h at x is equal to 3x minus 2. And then we are going to replace x with x plus 5. So h at x plus 5 is equal to 3. And instead of x, we're going to write x plus 5. So we're going to put in brackets x plus 5 minus 2. And now just think about it. You know what to do here. What's the next step? Well, if I want to simplify, I've got to expand or distribute this 3 into this bracket here. So let's do that. So sometimes students will once in a while start expanding this guy here. But remember, this isn't a variable h times another variable x. This is a letter that represents a function. So this is not h times x plus 5. This is h of x plus 5. So this guy gets left alone. So we have h at x plus 5 is equal to, and let's go ahead and distribute this. So we have this equal to 3x plus 15, and then we have this minus 2 on the side. And let's finish this up. We have h at x plus 5 is equal to 3x plus 13. So what that means is when we plug in x plus 5 into this function, into this linear function, we get the solution 3x plus 13. So let's take a look at D now. At this point, you know everything you need to know to answer all of these questions. So now this one looks a little weird. This is saying, what is h at 3 minus h at 1? So if a problem looks weird, just break it down. Like imagine, I can't cover it in the screen, but what if I just asked you for h at 3? Well, we know what that means. That means plug in x equals 3 and see what y equals. Okay, what if I just asked you what h at 1 is? Well, we know how to do that too. We know that x is just equal to 1 and what is y equal to. So if I can find them both separately, then do so, and then we can put them into the equation later. So first I'm going to find h at 3. Then I'm going to find h at 1, and then we're going to put it back into the equation together. So h at 3, we know, I'm just going to write out the original equation up here. We know it's h at x equals 3x minus 2. So let's skip a step. Can we just plug in 3 right into this equation here? So instead of x, I'm going to put in 3 minus 2. And I know that h at 3 is going to equal 7. And let's do the same thing for h at 1. So here's my red guy. And now we're going to do the blue guy. So we have h at 1 is going to equal, replace x with 1, and we have 3 times 1 minus 2. So our h at 1 is just going to be 1. So here's our solution for the blue guy. So now let's go back to the original problem. The original question that we were asked is find h at 3 minus h at 1. Well, I know what h at 3 is equal to. H at 3 is equal to 7. So I'm going to replace h at 3 with 7. And I know what h at 1 is equal to. H at 1 is just equal to 1. So I'm going to replace h at 1 with a 1. And I know I have subtraction in between. So this question is really just, what is 7 minus 1? And that is 6. So therefore, h at 3 minus h at 1 is just equal to 6. Let's try E now. Before we do together, just take a look at this. It looks weird. There's stuff going on here that we've never seen before. But see if you can point out a part of this that you know how to do. So if you take a look at it, hopefully you've sort of pointed out this part here, which is h at negative 3. We know how to find h at negative 3. So why don't we do that? I'm going to separate this, and let's first find h at negative 3, and then we'll put it back in there. So I'm looking for parts of this weird looking expression that I can recognize. So I recognize h at negative 3. So let's find that. Again, so if we plug negative 3 into our equation, we have 3 times negative 3 minus 2, which means that h at negative 3, when we plug in x, we get a y of negative 11. Okay, so now let's go back to our original expression, which is negative 2h at negative 3. So we know this part here. We know what h at negative 3 is. We know it's negative 11. So let's rewrite that. We have negative 2 times, instead of h at negative 3, we're going to write negative 11. So we're replacing that. And we're just left with this sort of easy expression, which is what's negative 2 times negative 11. And we know that's 22. So therefore, negative 2 h at negative 3 is equal to 22. And now we've got part E. This is weird because it's asking for x this time. For all the other examples in example 2, we've been given x. Now we're looking for x when h at x is equal to negative 4. What does this mean? Well, we know that h at x is the fancy way of saying y. So this is really y is equal to negative 4. So this is actually a really simple problem where instead of instead of plugging in for x and solving for y, we're doing the opposite. Now we're solving for x when y is equal to negative 4. So if it's easier to take this equation and write y here, then feel free and plug it in for negative 4. We're going to use function notation just so that you start to get used to it. So we have our original equation, which is h at x equals 3x minus 2. And now we're given h at x is equal to negative 4. So that's what we're going to plug in here. So we now know the value of h at x. So we're going to substitute it in. So instead of writing h at x, we're going to write negative 4 is equal to 3x minus 2. So we plugged in that h at x is equal to negative 4. Now we're just going to solve. So we are going to have negative 4 plus 2 is equal to 3x. Negative 2 is equal to 3x. Divide by 3. And we have x is equal to negative 2 over 3. So therefore, when y, or the value of the function, is negative 4, our input, x, is negative 2 over 3. So therefore, we have the point on this function. There must be a point, negative 2 over 3, negative 4, that exists on the function. We're going to try two last examples to test your understanding of function notation. Remember, by this point, you should be able to do all of these without me. So this question looks very similar to what we've done before. It's asking for f at 2, f at 0, and x when f at x equals 4. So it's very similar to what we've done. The only difference is that we're given a graph now. So we don't have an equation, we have a graph. So we could find the equation of this parabola and then solve it that way, but it's so much easier just taking a look at the graph. So to be able to use a graph to solve this, we really just have to break down, what is this asking? It's asking for the value of f at 2. So we know that this value here is just x. So what we're really given is when x is equal to 2, what's the value of the function? Which really means, what does y equal? So y, or the value of the function, the same thing. So when x is equal to 2, what is y? Well, take a look back at our graph. Where is x equal to 2 here? Right here. So we're going to bring it up until we hit the parabola. And x is equal to 2 when y is equal to 4. So that means that f at 2, meaning the value of the function at 2, is just equal to 4. Let's try the next one. So the next one says, what's f at 0? Well, we know 0 is just x. So if we rewrite this, it's really asking when x is equal to 0, now what's y, or what's the value of the function? So let's take a look back up here. Where is x equal to 0? Right here. And y is also equal to 0. So therefore we know that f at 0 is just equal to 0. And the last one, now we have, what's x? So we're looking for x when f at x is equal to 4. So we know that f at x equals to 4 means that y is equal to 4. So we can rewrite this as, we don't know what x is, so we don't know what x is equal to, but y now is equal to 4. So let's go ahead and look on the parabola. So we don't know what x is. Now we're looking at on the y-axis. So stop when y is equal to 4. It's right here. And what does x equal? Well, we've actually got two values of x. Y equals 4 hits the parabola 2 times. It hits it when x is equal to 2 and when x is equal to negative 2. So that means when y is equal to 4, x is equal to both negative 2 and positive 2. So this means that f at positive 2 is equal to 4, and there's a second solution. F at negative 2 is also equal to 4. Let's try our last challenging problem. So it just requires a little bit of algebra and an understanding of function notation. So here we're given two functions. Both of them are linear. This is saying if f at x is equal to 5 minus 3x, so the function f is equal to this, and g of x is equal to 4x plus 1. Again, you can just replace this g of x and f at x with y, but they're two different functions named different things. Find the value of x such that these two things hold true. So let's work on a first. So we're finding x, so we know that our solution in the end should be something like x equals. And these two things have to hold true. When does this function equal this function? Well, if you remember from grade 10, what that really means is we're finding the point of intersection. And if you don't see that, just look at it in terms of function notation. We have one side is equal to f at x. Well, we know what f at x is equal to. It's equal to 5 minus 3x. That's what we were told. And we have g of x on this side. We also know what g of x is equal to. It's equal to 4x plus 1. So we're going to do a quick substitution. We know f at x is equal to 5 minus 3x, and g of x is equal to 4x plus 1. So let's substitute. Instead of f at x, I'm going to write 5 minus 3x, copy the equals, and instead of g of x, I'm going to write 4x plus 1. And now, just use your grade 9 and grade 10 skills and solve this thing. We're supposed to be looking for a value of x. So let's collect the x's on one side and the constants on another. So I'm going to bring this negative 3x onto this side, and I'm going to bring this plus 1 onto this side and rewrite it. So I have 5, then minus 1 is equal to 4x plus 3x. If you want to solve in a different way, that's not a problem. So we have 4 equals 7x. Divide by 7, and we have that x is equal to 4 over 7. So what this really means is that these two functions are equal to each other when x is equal to 4 over 7, which means that this is the point of intersection. Let's take a look at the last example. Challenge yourself and try to do it on your own. See if you can pick out pieces of this that you could solve on your own, and then come back and check your answer. So remember the strategy. If you don't know what to do entirely, just look for parts of this that you could figure out on your own. So for example, hopefully you recognize that you can find what f at x plus 2 is. What that really means is we're just plugging in x plus 2 into this function right over here, f at x equals 5 minus 3x. And hopefully you recognize that g of x minus 1 is just plugging in x minus 1 into this equation right over here. So if it makes it easier for you, solve for this guy first, then this guy second, and just put it all in together. So that's what I'm going to do. I'm going to start off with finding f at x plus 2. And I really know that that just means that I am plugging in x plus 2 into this function right over here. So I'm going to put equals 5 minus 3, and instead of x, I'm putting in x plus 2. And we know how to solve this now. I've just got to distribute this through or simplify it. I'm going to rewrite what is f at x plus 2 is equal to. That's just equal to 5 minus 3x minus 6. And let's simplify this as negative 1 minus 3x. And let's box this. So now let's simplify what g of x minus 1 is. So we have g of x minus 1 is equal to, we know that this just means I'm plugging into the function g, the expression x minus 1. So every time I see an x, I'm going to replace it with x minus 1. So we have 4, and instead of x, I'm putting in x minus 1 plus 1. And we know what to do here. We're going to distribute this 4 into the bracket. So we've got g of x minus 1 is equal to 4x minus 4 plus 1. So we've got g of x minus 1 is equal to 4x minus 3. So now go back up to the original problem. We're trying to see when f at x plus 2 is set equal to g of x minus 1, what is x equal to? Well, we separated it. So we know what f at x plus 2 is now. We know it's just this value here. And we also know what g of x minus 1 is. It's just this value here. So now we can do a quick substitution. So instead of f at x plus 2, so let's rewrite this question. So we're really looking for f at x plus 2 is equal to g of x minus 1. I'm just going to put a line here so we don't get confused. I'm going to replace f at x plus 2 with negative 1 minus 3x. I'm going to replace g of x minus 1 with 4x minus 3. Okay, so instead of f at x plus 2, I've got negative 1 minus 3x is equal to g of x minus 1 is just 4x minus 3. And let's again collect like terms. So I'm going to send this guy over. I'm going to bring this guy over here. And I have negative 1 plus 3 is equal to 4x plus 3x. And we've got 2 is equal to 7x. Divide by 7, divide by 7, and we have x is equal to 2 over 7. So we know that these two functions are equal to each other when x is equal to 2 over 7.